So the next paper is called VelociTap, investigating fast mobile text entering using sentence-based decoding of touchscreen keyboard input. It's going to be presented by Keith Vertanen and from Montana Tech. And the co-authors are Haythem, Memmi, Emge, and Shyam, Reyal.
Okay. Thanks everybody for coming. So today I'm going to tell you a little bit about our recent work on VelociTap. And VelociTap is a sentence-based approach to touchscreen text entry. So a little bit different than what you're used to. Instead of maybe typing a character or a word and watching your recognition results, in VelociTap we're going to have users type an entire sentence, and then only then will we do sort of the auto-correction. So here's an overview of my talk. I'm going to tell you in the beginning a bit about some of our goals for the work, and then I'll describe for you the basics about how VelociTap works. So I'll talk about its touch model, its language model, and then the decoder search algorithm that kind of combines the two models together. And then I'm going to share with you 3 experiments we ran, and these experiments were designed to sort of improve the performance of the model, or as well as to increase sort of the usability of the overall approach. And I'll describe those as we go through them. So what were sort of our overall goals when we designed the VelociTap project? Well, first and foremost, we were kind of interested in seeing, trying to really get users to type quite quickly on their touch screens. And so we conjectured that perhaps, showing people intermediate feedback, showing them recognition results after every character or after every word, this might kind of slow people down. We wanted the people to go really fast and sort of to trust the recognition algorithm. And as such, we adopted a sentence at a time entry approach. So we're going to have people enter an entire sentence, and then only after that are we going to do the recognition on the sentence. And this is kind of a double whammy in that hopefully the users go really quickly, and it also gives the recognizer kind of the best chance of getting the answer right. All right, we're giving the most information to the recognition process. We wanted to test this on many users. Okay, so in the paper we're going to run, we have 2 pilots as well as the 3 experiments I'm going to describe today. And so there are well over 100 participants involved. We didn't want to train any kind of user-specific model that would require a bunch of adaptation data. Further, we didn't want users to have to learn a new keyboard layout or some new entry technique. So we're going to have them just tap on a familiar QWERTY layout. And finally, we were interested in one-handed or small keyboard use, so perhaps tapping on something like a smartwatch. And as such, we're going to focus here on people tapping with a single finger. Okay, so we're not going to look at 2-thumb typing or anything like that. Okay, so how does it work? So everybody in the audience gets to play a noisy tap decoder. Okay, I'm going to show you a sequence of taps over this on-screen keyboard, and your job is to try and infer the intended text. Okay, so is everybody ready? Here we go. Okay, maybe I'll play it one more time. Okay, ready, go. Okay, so any votes? What was the user's intended text? Have a nice day. Close. So have a good day is most likely, I would argue, the correct answer, and any reasonable model of the language. What was literally tapped, though, if you paid close enough attention, what was literally tapped was have a FOD day. Okay, so this F is off target, right? This F, this tap over the F probably should have been over the G, and there was only a single O. Okay, so maybe we didn't get 2 discrete signals on that O. Okay, so this is what we like. We like this probability distribution over the letter sequences given this noisy tap sequence. Okay, and as is kind of usually the case, we don't know how to do that, but what we do know how to do is use Bayes' rule, and so we can flip that around, and that's proportional to the probability under a touch model times a language model. And this is kind of analogous to things like speech recognition, only we have a touch model instead of an acoustic model. So those 2 parts of the model. First part is the touch model. VelociTap is currently using quite a basic touch model. We're going to center a 2-dimensional Gaussian at each of those key centers. Okay? VelociTap has two free parameters that let the x and y variance of those two-dimensional Gaussians vary, but there's essentially only two free parameters that control that across the entire keyboard. Okay? So the closer your tap is to the center of the key, the more likely that key is, but it can generate a likelihood for all the letters given any particular tap. So that's the first part of the model. Second part is the language model. We're going to use some pretty big language models. VelociTap uses both a character language model, so it's using a 12-gram. It bases the probability of the next character on the 11 previous characters. It's also making use of a word model. So every time VelociTap detects a word boundary, it's going to assess a probability of that word based on the 3 prior words. We're training this language model on billions of words of text from primarily found data sources, so things like Twitter, blog, social media. And if you've ever worked with sort of data like this, it's quite noisy. You have to do a lot of filtering, and so we have a technique we talk about in the paper, but basically we've optimized these language models to be good at short email-like messages, so things you would typically maybe write on your mobile phone. VelociTap, everything I present today, while VelociTap can operate on device, in this paper we're concerned with sort of the performance potential, okay, and the design aspects, and as such we didn't try and prune the language models to make them fit on device or optimize the algorithm to be performant on device. So we're going to proxy everything to a nearby desktop computer. Okay, so the decoding process. Here's an example. We have 3 different taps. Here's the example from before, the FOD. Okay, and I'm going to explain how the decoding process works using the idea of a token. In the beginning of the search, we're going to have a single token. It's an observation 1. Its job in life is to trundle along through the different observations and cross the finish line. Okay, the token would like to cross the finish line with the highest possible probability. So this first token, okay, the tap is over the F. So that token would like to generate the letter F and proceed to observation 2. In doing so, it would pay some penalty under the character language model. But of course, this isn't the only thing that can happen here, right? Maybe that's not the letter F, maybe it's the letter G, or maybe it's all the other letters of the alphabet, including space. Each of these would pay a penalty according to the character language model and generate a bunch of other tokens in observation 2. This red tap might have just been a mistake. Maybe the user didn't intend to actually tap something there. And so we might want that just to be deleted. We may allow the token to go to observation 2, but not generate any observation. And VelociTap has a configurable penalty for doing that deletion. Similarly, VelociTap has a configurable penalty for insertions, so we might insert all the letters. Maybe there was supposed to be another tap before the F, so we could insert all the letters A through Z, including space, and then that token remains in observation 1. At this point, the token is kind of all used up, okay, but he's generated a lot of children tokens in observation 2 and observation 1. VelociTap operates on, multi-core CPUs, so basically we have a bunch of threads, and they just randomly pick an observation, and then they pick the most probable token in that observation, and then do the same extension. So maybe we pick that token, we extend some stuff to observation 3, do some insertions, and so on, and then eventually some of our tokens start to cross that finish line, and we can keep track of their probabilities and keep track of what sentence hypothesis was the most probable. Now, kind of slight problem, right? This is a very short observation sequence, and we already have a lot of tokens bobbing around. Okay? We can't really afford to keep track of everything. And so similar to things like speech recognizers, we beam prune. We keep track of a beam width. If you're in observation 2 and you're too far away from the most probable token we've seen in observation 2, we're just going to kill you, okay? Maybe, this Z token here was going to be the comeback token of the century, but at some level we say, okay, you've become too improbable, we're going to prune you, okay? And so it's this beam width that lets VelociTap control the speed-accuracy trade-off of the decoding process. So that's how it works. Now I'll show you results from our 3 experiments. Each is designed for investigating a certain design aspect, which I'll talk about as I go through them. They all share the same basic experimental setup. So within subject design, we have 3 conditions: balanced, and that people are going to do a text copy task. And as I said before, everything's going to be proxied to a nearby laptop. Experiment 1, we wanted to baseline against a state-of-the-art commercial decoder, so we're going to compare against the Google Android keyboard. It turns out the Google keyboard can actually do this sentence at a time decoding. The approach you do is you just type a sentence, you just don't type any spaces. When you type the final space, it's going to try and infer all the positions of the spaces as well as correct any of the letters. Okay? And as you type, it's going to provide intermediate feedback of the nearest key. Okay, it's not going to do any decode until that last space, but it's going to show you the nearest key. We're going to compare that against VelociTap, operating in the same feedback mode. And then we conjectured that perhaps even showing this nearest key feedback was slowing people down. We're going to remove that in VelociTap and compare that. So I'm going to show you a short video of that. Okay, so here's the baseline. This is a Google keyboard, so I'm typing out this sentence. I'm not typing any spaces, and then when I'm all done, I'll hit the space bar, and it'll decode the whole sentence. There's VelociTap, same thing. The only difference is at the end, I will swipe up to do the decode. And then finally, here is VelociTap without visual feedback as I type. I still get clicky sounds and vibration. I just don't see anything until I do final recognition. Okay. Okay, here are the results. Entry rate on the left, error rate on the right. So entry rate was actually similar and quick across all conditions. While the no feedback condition, this guy on the right, was, our theory was this would be faster. It was slightly faster, but not significantly so. Okay, and so in the remainder of the experiments, we're going to stick with subjectively users. Some of them like no feedback, some like feedback. It was kind of mixed. And given that this is kind of providing this nearest key feedback is sort of status quo, we're going to stick with that for the remainder of the experiments. Error rates were low for VelociTap with or without feedback. These aren't significantly different. Google keyboard did have a higher error rate, okay, but to be fair to Google, they're decoding on the Nexus 4, so in the CPU and memory constraints of the device. And furthermore, the Google keyboard is sort of integrated into the existing word at a time interface. So the Google keyboard doesn't even in fact know for sure you want sentence decoding. Okay, so their job is kind of strictly harder than VelociTap's job. But VelociTap does allow us to explore this choice of always doing spaceless entry. So experiment 2, we're going to explore that choice. We're going to compare entry without any spaces. This in theory should be the fastest, right? You get to omit every 5th character in the entry. We're going to compare that with typing a conventional space bar between each word. And then we're going to compare it with swiping to the right. So instead of typing a space bar, you're going to swipe to the right anywhere on the screen. And our conjecture here is this should be more accurate because it provides very clear signal to the recognition process. And I'll show you a short video of that. So this is the normal spaceless version we saw last time. So I type the whole sentence, and at the end I swipe up. It will infer the spaces and correct the errors. So this is just typing a conventional spacebar between words. And then finally, here is the right swipe version. And I just swipe anywhere on the screen. It makes a swishy sound. Okay, but it won't correct anything until I swipe up at the end. All right, so here are the results from that. Entry rate on the left. Entry rate was similar for no space and space. Swipe was a little significantly slower. Okay, these are novice users, so perhaps they just weren't used to making this right swipe gesture, or maybe this swipe gesture actually takes them a little more time to actuate. Error rates were low for both space and swipe. Okay, but no space, what's going on here? Okay, so we've got quite a large box plot here. What's going on here, in this experiment we saw for a subset of our users, about 6 of them, VelociTap was persistently failing to insert those spaces. Okay, and so this drove the error rate up quite a bit. We wanted to investigate this, so we took the data from this experiment. So this is data from 24 participants. We split it into a training half and a test half. Okay, and what we did is, so VelociTap has around 10, 12 free parameters. Given this training set of 12 users, we had a lot more data in each of these different spacing conditions. We optimized those 12 parameters on the training data, and then as well, we increased this beam width. Okay, so this beam width I talked about, it turns out we were being a little too aggressive here, so the speed accuracy trade-off we got a little wrong. Roughly in a log scale. Oh, well, we beam prune based on a difference in log probability space, so I don't have a number for that. Yeah, so, but yeah, normally the decode though is taking on the order of, you know, a couple hundredths of a second on a desktop. Okay, so top left, okay, is that no space. So once we retrain or re-optimize those parameters, okay, increase the beam width, error rate is now low again in the no space, so that's good. What's really neat though is we were able to create a set of parameters that were good at each of the 3 spacing options. So basically we could allow people to omit spaces, type spaces, or swipe to the right and mix or match between sentences or within the same sentence, and the bottom right shows we get a very low overall error rate by doing that. So 2% in text entry, normally, often, like when you're doing a text copy task, people kind of mess up around 2% of the time. Okay, they spell things wrong, they miss words out, and so on. So this is still a little too easy. So in our final experiment, we wanted to see can we operate on a smaller form factor keyboard. So this would be useful on things like smartwatches, or it would be useful even on larger touch screens just to reduce screen occlusion. So I'll show you the final video of that. So we'll start off, this is normal portrait. The right is just a zoomed in version of the left, and I'm demonstrating I can mix or match those word delimiter options. Second keyboard is 40 millimeters. This is like a large format smartwatch. And this was quite popular. About half the participants like this just as well as the bigger portrait keyboard. Okay, so it feels quite good, and actually entry and error rates were pretty much the same as the normal portrait. This is the small version. Okay, so now the keyboard's about twice the size of my finger. This is similar to something like an Apple smartwatch. This was not as popular with all participants. Okay, so some participants found this quite challenging. Here are the entry and error rate results. So entry rate was quick and similar across all the conditions. Okay, so even as we went really small, people were still writing at, you know, something like 40 words a minute, even on these small keyboards. Okay, error rate was similar and low for normal and small, but we do see as we go to this really tiny keyboard, people started to have some trouble with error rates. And so this, remember, novice users here. With practice, certainly for myself, I can get below 4% on this small keyboard, but maybe it's a training process, or maybe you need like really small fingers or something. Okay, so just to summarize, okay, I told you about VelociTap, and what it does is it combines a really good language model with a really good search decoder. Okay, and even though we're just using kind of conventional status quo tap single finger on a QWERTY, people were able to go very rapidly and very accurately, even on watch-sized keyboards. So on our final block, novices were writing at over 40 words a minute on a 40 millimeter keyboard. So if you'd like to try it yourself, okay, we'll be demoing it tomorrow during the morning coffee break. So come to the interactive activity booth H2. And with that, I'd like to thank my awesome students and colleagues, and thank you for your attention.
So please come up to the microphone for questions. And one thing, I forgot one author. So Per-Ola Kristensson is also an author on this paper. And moreover, this paper received a Best Paper Award. So congratulations on the Best Paper Award.
Shuming Jai, Google.
Yeah.
Congratulations again. Isn't your central issue or problem you want to study is about giving word-level feedback or letter-level feedback versus sentence-level deferred feedback, if you will? I thought that's really the central issue you want to study. So I was a little confused about why you are doing all these different comparisons. And and what the point that was.
Well, so yeah,
But the real concern is that, so what is your conclusion about that? That is, what's the pros and cons of giving immediate feedback versus delayed feedback?
Yeah, and that's a great question. I think, definitely future work is to compare word-at-a-time recognition with, sort of this whole sentence-based approach. In this one, we really just looked at design aspects of, assuming we're doing sentence-based, let's look at the word delimiter and let's look at the potential at the small keyboard. But yeah, you're absolutely correct. What we need to do is do another study where you're seeing VelociTap popping recognition results every word and see what that is. And then really we need to do correction as well. So we have to support, what users really need to do is also do that correction aspect. So yeah, that's definitely interesting line for future work.
So as we were presenting, I thought you were going to compare with Google Keyboard, which give a word level feedback. It certainly wasn't optimized for sentence or that. It was just an extra fun feature it happened to have, and few people actually used this. Not many people actually know. And the other is just a small technical question. How do you combine the word level n-gram versus word 4 grams and character 12 grams?
Yeah, so we have two separate scale factors for the character language model and the word language model that we just multiply against the log probs coming out of each of the language models.
The two are multiplied? The two are, how do you combine the two?
Well, we multiply the scale factor times the log prob out of the language model plus the scale factor times the log prob out of the other language model. Yeah.
Xiaojun B from Google. I have actually, I think the one challenge of this first level decoding is that when the decoder should kick in to correct errors. So in your case, you use a manual like people swipe up or swipe right to let decoder take over. Do you have any comments like when you input a long sentence or multiple sentences, when they will do this kind of swiping? The first question. Second question is that I feel when people switch from typing to swipe, it actually breaks the rhythm of typing. I'm wondering whether any user have comments about how they feel about they mix this typing with the swiping. Thank you.
Okay, so the first question, I just forgot the first question.
Yeah, first question is that like when user they manually swipe to kick off to start the first level decoding.
Yeah, so you could imagine, right, doing something. Is your question like? I mean, you could imagine doing something like if they pause for so long, then push the recognizer. Is that what you're asking?
I'm asking, for example, if you input a sentence with like 10 words, usually at which position user will start doing? They will swipe up to.
Yeah, I think that's very interesting. I mean, because you could imagine people doing some sort of like phrase. They do a grammatical phrase and then swipe up.
I mean, the whole sentence. If I have a long sentence like have maybe 10 words, they will wait. They will usually wait until the end of when they encounter like period key, or they will do swiping, or they might sometimes do maybe swiping in the middle of the sentence.
Yeah, I mean, it could support that, but it's not something we currently looked at. Yeah.
So my second question is like when because they switch between type and swipe. Do users have any like do they have any comments about when they alternate
swipe
between
versus
two modes?
space. They did have their subjective feedback in the paper. You can check. But yeah, it was mixed. Some people liked it and thought it was really cool, and some people said, I like spacebar. Most people said, I like spacebar. That's what I've done. That's what I know. So novice users. So,
Thank you.
Thank you.